Hello dear learners, we will continue our discussion on the derivation of governing equations for understanding plasma as a fluid. So in the last lecture we have seen that plasma can be considered as an entity of two interpenetrating and non-interacting fluids, one electron fluid, another ion fluid. Okay. Now let us bring the relevant equations to constitute the set of governing equations. Okay. So let us start with the charge density, because it is a charged entity. The charge density, the charge per unit volume can be rho, which is Ni Qi plus Ne Qe. Ni is the number of charged particles or charged number of ions per unit volume. Qi is charge per ion, and similarly Ne becomes the charge number of electrons per unit volume, etc. And the current density, because there is movement, the current density can be written as J, which is equals to Ni Qi Vi plus Ne Qe Ve. Let us call this as equation number 1, this as equation number 2. So these are the basic properties of plasma. Okay. And then we have the momentum equation, Newton's second law, momentum equations. So we will write equation for electron and ion separately. Okay. So we will write it as Me Ne dou Ue by dou T plus Ue dot del times Ue is equals to minus del Pe plus Qe Ne times E plus Ue cross B. All the other forces I have already neglected on the right hand side. Let us say we call this as equation number 3. What do you see here? Ue is the electron velocity, okay, and Pe is the pressure gradient in the number of electrons, okay, only within the electron fluid. E is the electric field, B is the magnetic field, etc. So we can also write the equation for the ion Mi times okay. So these are the momentum equations for electron and ion fluid. So what additional equations will we require apart from these? Because plasma is a collection of charged particles and a very active electrodynamical entity, we will need the electrodynamics equations or the Maxwell equations. Maxwell's equations. So we will write them as del cross B is okay. Let's say we call it as equation number 5, and 1 by mu naught del cross B is equals to Ni Qi Ui plus Ne Qe all right. and del dot B is 0, and epsilon naught del dot E is equals to N, the Gauss's law, Ne QE. We said this is 6, this is 7, and this is 8. Right. So, the momentum equations, the charge density, current density, the 4 Maxwell equations. So, what else we would need in addition to these equations? We would need the continuity equations, which are basically the conservation of mass. So, the equations of continuity, which are dou Ne by dou t plus del dot Ne ue is equals to 0. Let us say we call it as equation number 9, and dou Ni by dou t plus del dot Ni ui is equals to 0. So, we already have 10 equations expressing various aspects about the plasma. Okay, and then we can have the equation of state or thermodynamical quantities or the kinetic properties of plasma expressed in terms of equation of state, which are Pe is equals to Kb Te Ne, and Pi is Kb Ti Ni. 11, 12. Right. And what the physical properties which have not been covered in these equations, you can consider the density has not appeared yet. So, we can write it as Pe is a constant times rho E times gamma. Gamma is the ratio of specific heats, and Pi can be written as a constant times rho I times gamma. So, we call it as 13 and 14. Now, let us look at all the variables which have appeared in these equations. Variables which are Ne, number of electrons per unit volume, Ni, number of ions per unit volume, Pe, the pressure of electron, Pi, the pressure of ion, rho E, rho I, Ve, Vi, the electric field, the magnetic field. Right. So, this many variables are there. Anything else that we missed? Look at the equations. Yeah, the charge density, of course, it is. Then you have charge density, current density. Yeah. So, all the variables are listed here. Some of these variables are scalar in nature and some variables are vector in nature, which means combinedly these variables are enough to express plasma or to characterize plasma. So, if you are talking about a plasma, these variables, some variables are properties of plasma, like number of particles, charge densities, all these things. But some other variables represent or tell you the behavior of plasma. What is its velocity, how it is getting affected by the electric field, by the magnetic field, and how these two fields are interconnected, etc. Right? And how the fields can give rise to other electromagnetic properties, etc. Right? Now, if you look at these equations carefully, equation number 3, 4, 5, and 6. Equation number 3, 4, 5, and 6. These are vector equations. right? So equation number 3 has the velocity, electron velocity, which can be written in 3 components. So this equation number 3 can be written into 3 equations, 3 separate equations for the ith component, for the jth component, for the kth component. Or even the magnetic field that appears here is also a vector, right? So you take the cross product of this, UE cross B, then you will be able to write all the 3 equations. Right? Similarly, equation number 4 is also a vector equation, so which can be written again in 3 different components. Equation number 5, a curl equation, which is again a vector equation. Equation number 6, which is again a vector equation. So you have 3 equations, 3, then you have 3 here and 3 here, right? And then the other equations are scalar equations. The charge density is written as this. The current density is just a constant scalar equation. Equation number 7 and equation number 8 among the Maxwell equations are also scalar equations. So you have, and then you have the continuity equations, which are again scalars, del dot, scalar equations. And then the equation of state, which connect the thermodynamical properties of plasma, are also scalar equations. So pressure written in terms of number density or pressure written in terms of density are identical. So if you know the pressure, by using other variables you can calculate the density, etc. So you don't have to use both the forms at the same time. So how many number of equations do we have? So you combine the vector equations, include the number of components, then you would get the total number of equations or the total number of variables that you have in this picture will be 16. 16 including the scalar components. Scalar components as in Ex, Ey, Ez, Bx, By, Bz, Ux, Uy, Uz. Okay. Ne, Ni are the variables. Pi, Pe are again the variables. 3 velocities for electron, 3 velocities for ion. Electric field 3 components, magnetic field 3 components, right? So put together there are 16 scalar unknowns. See, because you are writing the set of equations which are required to understand plasma's properties or evolution of plasma's physical variables, you need all these equations. So these equations cover all different aspects of plasma. They cover the thermodynamical properties of plasma, they cover the electrodynamical properties of plasma, everything. But how many number of equations are there? The variables. The minimum number of variables that you require to understand plasma completely are 16. So these are the variables which you need. Or if you want to solve these 14 equations, then the purpose of solving these 14 equations is to, not 14 equations actually, these are in number, but when you write the component equations, it will be different, it will be a different number. So these 16 unknowns can be known by solving these coupled equations, of which if you try to solve one equation, you would be required to solve another equation and obtain the solution and substitute into this equation, then you'll be able to solve. But then again, you cannot solve this equation, you cannot solve the second equation before you solve this equation itself. So they are coupled in nature. So these equations can only be solved simultaneously. So you assume initial solutions and then you solve these equations. And if you hit convergence, then the initial conditions that you have assumed would be valid. Okay. So there are 16 scalar equations, scalar unknowns. and the total number of equations are 18. How do we get 18? We can see this is 3 component equation, right? So you have to take 3 equations, vector equations, and you have the other equations, which are the del dot B and del dot E, and then you have the equation of state and the continuity equation. So there is a mismatch between the number of equations and the number of scalar unknowns. So how much? We have 2 additional equations. 2 additional equations are there. So if we have a situation in which there are number of equations equal to the number of unknowns, we can solve them and the equations are good to go, right? So we have to relook at the set of equations and try to figure out if there is any redundancy, or if any equation can be a simplification of another equation or things like that. So in that case, we don't have to use both the equations. It would be sufficient if we know only one, if we have one equation, because the other equation is basically a subset of the first equation, right? So in that case, let us look at the equations and then we should be able to figure out. So let us write down the unknowns first and also write down a consolidated list which tells you all the equations. Okay, so let us say we have the unknowns or variables NE, NI. There are 2 variables here. VE, velocity of electron, and velocity of ion. Because it is a vector, we have 6 unknowns here. Pressure of electron and pressure of ion. We have 2 unknowns here, and then the electric field, including its components, we have 3 unknowns, and the magnetic field, similarly, including the components, we have 3 unknowns. This is as far as the unknowns is concerned, and let us look at the equations. We have 2 continuity equations, one for electron and another for ion, so we have 2 in total. We have momentum equation for electron. We have 3 equations because it is a vector equation, and then we have a momentum equation for ion. Again, we have 3 equations, and state of equation of state for electron and ion we have 2, and then we have how many Maxwell equations? Maxwell equations are 4, out of which 2 are vector equations, so that becomes 6 plus 2 becomes 8. So we have in total we have 18 equations, and in total we have 16 unknowns, right? Now it becomes important that we try to reduce the number of equations so that it matches the number of unknowns, because we want a consistent behavior that can be derived from the governing equations. So let us look at this equation, del cross B. Let us look at this equation, which is del cross E is equals to minus dou B by dou T. Let us take a dot from the left with del. Okay. Del dot del cross E is minus dou by dou T of del dot B. Divergence of curl, we know that it is 0. So dou by dou T of del dot B is equals to 0, which means this equation is essentially conveying the same information that we know with the help of another equation, which says that del dot B is equals to 0. So that means we can get rid of del dot B is equals to 0, because the information that it provides is already there in another equation. Okay, we'll convey, so del cross E conveys what del dot B actually conveys. And another equation that we can think of is del cross B is mu naught j plus 1 by c square dou E by dou t. Let us take a dot with del from the left. So we can write it as mu naught times del dot j plus 1 by c square dou by dou t of del cross E. Okay. So we know that from the earlier equation, the divergence of curl simply becomes 0. So we can write it as mu naught times, or we can write del dot. We can expand this and write mu naught times qi times del dot ni vi plus qe times del dot neqe plus 1 by c square dou by dou t of del dot E. It should be a dot. All of this equals to 0. We can write it as 1 by c square times epsilon naught times minus ni qi minus ne qe plus 1 by c square dou by dou t of del dot E is equals to 0. Upon simple substitution, simple algebra, we will get this as equal to 1 by c square dou by dou t of minus rho by epsilon naught plus del dot E is equals to 0. So, you look at this term which appears within the bracket, it is nothing but the Gauss law, which is del dot E is equals to minus rho by epsilon naught, which means the information that we had in another equation is available in the fourth Maxwell equation, which is written in terms of the displacement current, right? So, which means that, so by removing these two equations, which are superfluous in nature, we know that the total number of unknowns is equals to the total number of equations. So, we have a consistent picture, or by solving these equations simultaneously, we can pretty much obtain all other properties of plasma. So, we have seen what is a two fluid plasma, we have made some assumptions, and we have now derived a full set of equations which are required to understand the complete behavior of plasma. Yeah. So, in addition to the governing equation, we will discuss what is called as a consequence of these governing equations or fluid description of plasma. We will discuss what is called as the magnetic pressure. So, magnetic pressure is very important when you are trying to understand the balance between the solar wind and the magnetosphere. Okay. So, let us consider a neutral plasma. Let us consider a simple or neutral plasma in which the electric field is taken to be 0. Okay. So, if we consider the ideal MHD equations under the steady state or in equilibrium, we can pull the Maxwell equation or pull the momentum equation that we have derived just now as Ne Me plus Ni Mi times dou um by dou t is equals to minus del p plus j cross b. J is the current density, B is the magnetic field, P is the pressure term, right? Now, if you take the steady state to be existent, This means the velocity is not changing with respect to time. So this term becomes 0. We can write it as J cross B is equals to del P. Let us say we call this as equation number 1. So in addition, from the Maxwell equation in steady state, we know that del cross B is mu naught J plus a time varying term. So because we have assumed steady state, we can write del cross B to be equal to mu naught J, and we already know that del dot B to be 0. We call this as 2, we call this as 3. What have we done? We have just taken the momentum equation and we have assumed steady state in that, and we realized for the steady state to occur, the curl of J and B, the current density and the magnetic field, should be equal to the change in the pressure. Delta P is the pressure gradient, or if you consider fluid, within fluid, if there are two regions which are differing by pressure, delta P gives a measure of the gradient between the two regions. So from equation number 1, the pressure gradient force, J cross B is essentially the Lorentz force. So the pressure gradient force for the steady state should be equal to the Lorentz force. Right. Now, if this equality has to be maintained, the curl between J and B will be in a direction which is perpendicular to both J as well as B. So we can assume that, so the resultant of J and B, the vector product of J and B, will be perpendicular to del P. So J and B must lie on the surface of a constant pressure. So J and B, so you can think of constant pressure surfaces. So one is a low pressure, another a high pressure. So the gradient is towards the high pressure, and let us say this is the direction of the gradient del P. If we take the reference to be this to be x and let's say y, okay. So we can eliminate from equation 1, we can eliminate J. Okay, so J, we know that J is equals to 1 by mu naught times del cross B. Take a curl with B on the right, we can write 1 by mu naught del cross B is simply J cross B, which we know that E is equal to the pressure gradient. So del P, so this one using 1, del P is resolving the triple vector product, we can write 1 by mu naught B dot del times B minus half del B square. Rearranging the terms, we can write del of P plus B square by 2 mu naught is equals to 1 by mu naught times B dot del times B. So this term that appears on the left hand side, P plus B square by 2 mu naught, this should be in the dimensions of pressure, right? Or if if B is not changing, if the magnetic field is not changing spatially, or when it is very small, we can neglect the right hand side. That means that B is not changing with respect to the space. So we can say that this quantity becomes 0. So in those situations, we can expect P plus B square by 2 mu naught to be a constant, or this term B square by 2 mu naught is called as the magnetic pressure. So magnetic pressure becomes particularly important if you are trying to understand the motion of solar wind or interaction of solar wind with the magnetosphere. So you can define a ratio between the magnetic pressure and the kinetic pressure, and depending on this ratio, we attribute several properties to the plasma. Okay, so this was some discussion on governing equations for a two fluid plasma, and how, as a consequence of that, we can discuss or we can understand the magnetic pressure of plasma. So, plasma, by the virtue of its magnetic field, exerts some pressure, and how, by the virtue of its number of particles, the kinetic pressure uh, balances or becomes important with respect to the magnetic pressure, defines many interesting properties of plasma, which will be a topic of discussion for lectures ahead.